Hello, my name is Austin Stottlemyre, and I'm the current director of Cowboy Rocket Works, the high-powered rocketry team here at Oklahoma State University. This year, our goal for the Argonia Cup competition is to test the effectiveness of our simulation software and to also test our manufacturing techniques of rocket components such as body tubes and payload systems. This con-op shows that our team has taken a simple approach to meet the competition challenges. We will overshoot the required height to ensure sufficient altitude despite unknowns like wind on launch day. We will then use a drogue chute to control descent and deploy the main chute at a low altitude to minimize drift and help land near the target. Now a few members of the team will go over the details of how we plan to achieve this.
Hi, my name is Garrett, and I'll be telling you guys a little bit about the propulsion system for our Argonia Cup rocket. First of all, we'll be using an Aerotech L1000W, and that's a DMS motor. It's a 54mm casing, and it'll be slightly longer than the one I'm holding here. And obviously it'll be a disposable motor and not a reloadable motor like this one. The total impulse of this motor is 2,700 Newton-seconds. The peak thrust is 1261 newtons, which is around 300 pounds, and the burn time is 2.7 seconds. You can see here on the thrust curve, it's a fairly neutral burning motor, which should help us out and not give us many surprises during our flight. The reason we're going with the DMS motor is to try and mitigate any risk associated with the motor in our launch vehicle. Whether that be CATO or just issues assembling the motor on the field, we want to try and avoid any of those and focus everything on achieving our altitude and achieving the payload recovery, which are the two main objectives. We do have a backup plan to this motor, and that is using an L850W, which is a reloadable motor. And the only reason we think we would need to use that is if we're not achieving the altitudes we're expected on launch day. Right now we're supposed to hit around 8,500 feet, so we should be good, but we did have a contingency plan built in the case that we are cutting altitude for some reason.
My name is Jordan, and I'll be talking a little bit about our payload systems. We have designed an additively manufactured golf ball holder out of ABS that will safely secure the payload inside of the electronics bay tube. The goal of this design is to safely secure the golf ball upon ascent of the launch vehicle and then deploy it at its predetermined altitude. With payload recovery being the main objective of this competition, it is critical that our golf ball stays secure during ascent of the rocket and then deploys with no issues. Our additively manufactured design should help us achieve these goals.
My name is Caitlin, and I will be telling you a little about the structures portion of our Argonia Cup rocket. This year we are working with our own composites, and as a team we are coming close to being able to produce an entire structure of a rocket ourselves. We have achieved this by rolling our own airframe tubes and motor mount tubes on phenolic mandrels. We are also making our own retaining rings and fins by successive layers of fiberglass upon each other until sufficient thickness and strength is obtained. These processes have been tested and flight proven at the Argonia launch site earlier this year. The Argonia Cup, we will show our capabilities of manufacturing and will be used as a learning and teaching tool to show other members how to continue the work.
Jordan here again, and this time I will be talking a little bit more about our recovery system. Our payload design, placed within the electronics bay of our rocket, will be attached to the outer bulk plates using bolts. While not structurally integral to our launch vehicle, maintaining possession of the golf ball during the flight is critical to our performance in this competition. Our electronics bay will be composed of an additively manufactured electronic sled carrying two separate altimeters and an inertial measurement unit for data logging throughout the flight. In order to mitigate as much drift as possible for our launch vehicle and our payload, we plan on deploying a drogue parachute at an apogee of around 8,500 feet above ground level and our main parachute at an altitude of around 800 feet above ground level. This will mitigate as much drift as possible for our payload in order to ensure that it lands as close as possible to our target zone. With additional monitoring of the weather conditions, namely the wind conditions, we plan on fine-tuning the recovery system as needed.
We modeled our rocket using the Open Rocket simulation software. After running the program, we learned our rocket should reach just over 8,500 feet and have a total drift of just under 1,000 feet. This year, Cowboy Rocket Works aims to not only win the Argonia Cup competition, but to also prove ourselves as a quality rocketry team and establish a reputation of success here at Oklahoma State University. We look forward to seeing you on the launch field, and go Pokes!